Hello guys, this is Code and Code, and this is the fourth lecture of this number theory series. And in this lecture we are going to talk about binary exponentiation. So binary exponentiation is basically when you are given to calculate a raised to power n, and it is also known as exponentiation by squaring. So you are given two numbers, two integers a and n, and you have to calculate a raised to power n. Then there are two approaches. One is of course brute force and the other one is binary exponentiation. So binary exponentiation allows you to calculate a raised to power n in log n time complexity. So let's see what we would do in brute force approach. You are given base, you have to calculate base raised to power n. So what we can do, we would initialize result to be 1 and then run a loop from 1 to n, and each time we would multiply base with result and finally we would return result. This is pretty straightforward, right? No problem in here, nothing. It's just simple and easy. So the overall complexity, of course, as you can see, is big O of n, that is linear in n. So the binary exponentiation, I would explain you through an example. So suppose you have to calculate 2 raised to power 13. We have two variables, result, which would be the final result, base and power. Now what this represents here is that this part is calculated, and all you have to do, calculate this part and finally multiply this calculation to this, and that would be the final result. The final result would be 2 raised to power 13 multiplied by 1. This doesn't make sense, right? I know, but it would. Just bear with me. So since power is odd, what we can do, 2 raised to power 13 we can write as 2 multiplied by 2 raised to power 12, right? So using that fact, the 1 2 that was there, 2 into 10 in the expression 2 into 10 2 raised to power 12, the one base I have multiplied with result. Now all we have to do is calculate 2 raised to power 12, right? So when the power is odd, what we can simply do is simply multiply the result with the current base. So all we have to do is calculate the even power of the given base. Now if you calculate 2 raised to power 12 multiply it with the result, then we would find the final result. Now since power is odd, what we can do is 2 raised to power 12 is same as 4 raised to power 6. So what we can do, we can square the base and divide the power by 2. So power gets half and base gets squared. That is why it is also known as exponentiation by squaring. So what you do, you square the base and divide the power by 2. So just assume if you had to calculate 2 raised to power 100 or 2 raised to power 1000 for now. So if you have to calculate 2 raised to power 1000, then 2 raised to power 1000 is same as 4 raised to power 500. So you see, you have saved there 500 multiplications. Same goes here. If you had to calculate 2 raised to power 12, you have to run a loop from 1 to 12, but now we have to run a loop till 6 only, not till 12. Now again, 4 raised to power 6 is same as 16 raised to power 3. You see, result variable is not being changed, only base and power are being changed. So 4 raised to power 6 is same as 16 raised to power 3. So we have squared the base again and reduced the power by 2 each time. Now you see, the power becomes odd. Now what we can do, 16 raised to power 3 can be written as 16 into 16 raised to power 2. So the first 16 we would multiply it with result, and then all we have to calculate is 16 raised to power 2. Now since power is again even, what we can do, 16 raised to power 2 is same as calculating 256 raised to power 1. So we would whenever you see the power even, you divide the power by 2 and multiply base with itself, that is, you square the base. And now since the power becomes odd, you multiply base with result and then reduce power by 1. Now as soon as the power becomes 0, this is your final result. So you see, whenever we see the power odd, we divide it. So at most every second operation, the power gets reduced by half. So this is what gives you a complexity of log n with base 2. So if you see the implementation, that is easy too. You have to calculate a raised to power n. You initialize result with 1, and while n, which means while n is non-zero, that is while n is greater than 0, if n is odd, of course you would multiply a, that is base, with result and reduce n by 1. Otherwise, if it is even, what we do, we divide the power by 2 and multiply base with itself, that is we square the base. This is simple, and then finally you would return the result. And this is it is having a complexity, sorry, it is having a complexity log n because of this, because at most every second operation power gets reduced by half. In fact, you can make it in such a way that in every operation power gets reduced to half. All you can do is simply remove this else statement. So in every case it would be reduced by half, because if it is odd, then after reducing the power have to be reduced by half. If it is not, then it have to be reduced by half anyways. So you can simply remove the else, and this would work fine as well. So this is modular exponentiation. In some cases you have to calculate a raised to power n modulo some prime number p. So in that case you can simply simply change code a bit, and you can say, since when n is odd, you have to multiply a with result. So what you can do, result is equals to result into a, and then take a modulo of it. Rest is same goes for this. Since you have to square a, so you can write a is equals to a into a mod p and divide n by 2. That's all you have to do, and finally return the result. So this is modular exponentiation, because you have to calculate a raised to power n modulo p. So this was modular exponentiation, or exponentiation by squaring. So it runs in log n time. So in next lecture I'll be taking 1 or 2 example problems of it, and till then just keep coding. Thank you.